One of the current hot topics in physics right now is the question of how far should you go in theory, in fundamental theory. And it seems to be the case now that some theories are so complex that there seems to be no possible way of actually, verifying them. And so my example of this would be string theory, which is an attempt to unite gravity and the quantum theory, and there is no such formal connection between the two theories, but string theory is something that is thought to be close to that theory, and so many of our colleagues in theoretical physics work on this. And one of the problems is, this is being discussed a lot in the literature now, is they have been unable to come up with any empirical tests. And one of the more bizarre things that has been happening is that rather than come up with empirical tests, one builds theoretical implications which at first sight seem very convincing. And one of them, for example, takes us into what has been called the multiverse, right? That there may be a whole lot of universes out there. So I know you're more of an advocate than I am of the multiverse, so maybe we should talk about that a bit.
Sure, I'll be happy to talk about this. I wouldn't call myself an advocate. I would say, I'm open-minded to that possibility. But let me perhaps first comment on string theory in general. I'm not a string theorist myself, yes, so I should preface that. I follow it, from a certain distance. And you're absolutely right that, well, our feeling, right, as physicists has always been that we should try to make the theory as simple as possible, to explain as many as possible phenomena with as few as possible assumptions. With a few laws, we want to explain everything. Hence these types of names like theory of everything and so on, when of course are very misleading names, because we're only talking about very fundamental physics. It's not as if, we explain the human brain or anything with this theory. So you pointed out that one of the problems has been, how do you unify our theory of gravity, which is general relativity, with quantum mechanics? Each one of these theories appears to be working fantastically well, but on very different scales. Quantum mechanics on the subatomic scale, gravity on the large cosmological scales. The problem to find a theory that unifies the two has been really, really hard. And for a few tens of years now, we have come to think, I think you also shared this feeling, that string theory was, and maybe even still is, our best candidate as trying to do that. But unfortunately, it has not managed to produce many testable predictions. In fact, I would argue that perhaps has not generated anything, even though this statement is a little bit qualified in the following sense. There is the Bekenstein-Hawking theory of black holes, of the entropy of black holes, which relates the entropy of a black hole to the surface area. And two string theorists, Andrew Strominger and Qumrun Vafa, actually calculated the entropy of black holes from states, counting states within string theory, and they actually came up with the same formula. Now, you can say, yes, but we have not yet even verified experimentally the Bekenstein-Hawking formula, so it's not exactly that we have produced something that is a testable prediction, but at least the fact that these two things agree, gives you some confidence that maybe they
Sure, that's very elegant, but that's what you could call, non-empirical confirmation, or non-empirical evidence is even better. And at some point, that's important, but you just wonder, just how you balance that against empirical evidence for something, which is what we're used to in physics, in science. And that's what, since the time of the natural philosophers of ancient Greece, ever since we've moved forward and learned more about the universe, by doing experimental verification, which leads us to making predictions and models that we can then further test. And this is now something that we seem to be moving away from as we get further into string theory and
right. So not entirely moving away in the following sense, at least, that I think it would be extremely hard to verify, for example, the existence of Bekenstein-Hawking radiation in the case of black holes themselves. However, physicists have designed some clever experiments where they have shown that there are some physical conditions which, at least from a mathematical perspective, resemble very much Hawking radiation. A little bit like, if you look at water flowing in a river and then falling in the waterfall, and you take some fish that try to swim against the stream, that has been shown from a formal perspective to be very similar to escaping from a black hole. And then there are people who design physics experiments to test those types of situations. Now, it will not show that Hawking radiation per se exists, but at least it would show that something that is formally similar exists. So it's not, I think, that people have given up on confirmation by experiments or observations. It's just that those appear to be very hard.
That's right. But I think, if you like, the acid test is, will Hawking get the Nobel Prize for the discovery of Hawking radiation? The answer is not until we discover it. And no matter how good our analog experiments are, that won't cut things really. So getting back to string theory, I think one of the problems is there is no such thing as a string theory. There are many, many string theories, and it's more like an entire framework. And so it's something that is a bit like a moving target. So that also I find, a bit disillusioning if you ask, can I ever test
it? I find it
this?
disturbing too.
And it's very, very hard to even come up with these empirical tests. To establish this. Yeah.
You're right. I find this very disturbing too. I mean, string theory has been fantastic in terms of generating new mathematics and, very interesting mathematical directions. But you're absolutely right. Until we will actually have a testable prediction, we will never know whether that's even the right direction, let alone the right theory.
So here's one beautiful prediction in a very particular subset of string theories that they exist in these higher dimensions. So when they compactify down to our 3+1 dimensional space, whatever, they could leave behind strings of the matter from the higher dimension, but these strings exist in our space, in our universe. They're called cosmic strings, and they whiz around at the speed of light at this incredibly high density but incredibly tiny size. But they do leave a trace behind of gravitational radiation, gravity waves. And so indeed, the chase is on now. People are constructing giant arrays of telescopes to search for these things. So that's an example of something that's, one tiny subset of string theory that has a very nice prediction that is something that we could someday empirically confirm.
I completely agree, yes. Yeah. And there have been searches for a variety of topological defects, of the type of string, otherwise, people have searched for monopoles for a long time, and there has even been one suggestion of a detection of a monopole, but nobody really believes that. Yes, you're right. I mean, if we will find some sort of confirmation, it will be fantastic. At the same time, there are people who would tell you that, I'm sure you heard this phrase, that string theory is a 21st century theory that somehow by accident fell into the 20th century, which wants to say that we are still in the very early stages of understanding what that theory really means, and that, maybe there are still in the future some developments that, maybe we can await, which will actually produce some testable experiments or observations. I'm not holding my breath, but it's not impossible, I think.
Yeah, so the other big development, of course, in our knowledge of the universe has been the discovery that it's accelerating, that space-time is accelerating, and that this is due to the presence of what we call dark energy, which, as you know, is, in some sense, was a surprise when it was discovered, because for the predictions from particle theory, for what they were worth, if there were any dark energy, it should have been very, very much larger in value than the value we actually measured. And of course, to explain this bizarre anomaly, one common idea is that there are many, many universes out there with these more natural values of dark energy, and the one that we happen to be in, of course, has this very small value. So I find this another example of a theory that's totally untestable, and not really worthy of the name of theory in the physics, in the usual, sense of physics.
Yeah, well, what we like to talk about fine-tuning and so on. And fine-tuning appears unnatural to many physicists, so they want to solve this unnaturalness thing. And indeed, one of the suggestions has been that, okay, if you have a very large ensemble of universes, then those could have a wide range of values for a variety of parameters, one of them being the cosmological constant or this dark energy, and therefore we certainly would have to find ourselves in one that is consistent with our existence. We cannot find ourselves in a universe which has a cosmological constant that's so large that galaxies could never have formed. So you're right. I mean, there are many physicists to whom this raises the blood pressure, just the mention of this possibility, because it does fly in the face of a long tradition of being able to explain from first principles every fundamental theory that we want to employ. The question is whether or not our assumption that you can explain everything from first principles is in itself valid. I mean, yes, we've had a long history of successes with that, but there is nothing ever to have promised us that we will always be able to do that. And by the way, unifying gravity with quantum mechanics may be one of those things. I mean, maybe we will never be able to do that. Nobody guarantees us that, we will be able to do that. So at some level, you're right. I mean, relying on the multiverse sounds a little bit like giving up on that concept that we have grown up with, that, we should be able to explain everything from first principles. However, that entire premise relies on another type of thing that we also are aware of, which is that there is no way at any given time, you can always know these things when you look backwards in history, but at any given time, there isn't a good way to tell you which things are really fundamental in the universe and which things are accidental. I mean, we can explain planet formation based on the laws of physics. Well, we don't have a good theory yet, but we in principle, yes, can explain star and planet formation based on the laws of physics. However, to say in advance how many planets are going to form and where are they going to be and so on in any given planetary system will depend on the very specific conditions in that environment. It's not something that will come out from first principles. Until you understand that that's the situation, you may be in a situation where you think that something is fundamental when in fact it isn't. and it's just a random variable. The people who try to speak in favor of the multiverse would argue that the value of the cosmological constant may be such a random variable. Is that right? I don't know. I have no idea. But, you know, I'm willing to keep an open mind as long as you say some predictions will be made which can be tested.
So I guess the thing that worries me most about this rush among many of our colleagues to the multiverse is that you arrange all these other universes, so there's some enormous choice between all the possible values of the dark energy parameter. Some have enormous dark energy, some have very little, some have just the right one that we have in our own universe. That's just our unique universe. It seems to me that the advocates would argue this is the simplest explanation of this apparent contradiction between the predictions of, if you like, the Big Bang theory, the beginning of the Big Bang, this high energy state, and what we observe today. You just have to throw in some random variable. On the other hand, I'm tempted to think of Occam's razor, which to me makes this sound incredibly complicated. You're just throwing in a nearly infinite number of other universes, 10 to the whatever, 500. Some would argue an almost infinite number out there just to explain our one universe. Don't you think that's being rather extravagant? Or
it may be extravagant. It may be extravagant, but at the same time, there is this enormous fear of fine-tuning, which you have to say, well, how do I explain this unnaturalness? And this is where some physicists have come to conclude that the only way to explain this unnaturalness is to say that you have this large ensemble and you happen to be in one that has these values, instead of saying, well, I can actually explain all these different values. And it's not just the cosmological constant. It's, in principle, all the mass ratios of elementary particles and, all these other things, the mass of the Higgs that was recently discovered and so on. That's the only way for me to try to gain an access on all of this complexity, which is not unnatural. Again, I think we should wait and see what happens. I think either this assumption of the existence of the multiverse will get some additional support because of some testable predictions, or it will remain in this limbo where some people will think that explains something, the fact that you have this large number of universes, and some people will think, no, we just don't know how to explain it, and that's it.
I mean, I don't even see it as a real explanation of anything, because once you throw in all these other constants of nature that you may say are assigned randomly into your initial hyperspace or whatever, then you're still left with huge numbers of possible. We don't have a unique universe in the sense that you can have large variations in all of those things and still have a universe that would, in which galaxies form, planets, whatever. It wouldn't be no different from ours. So it's not as though you're solving the problem of explaining the actual values we have, because you're not. They could be very different from the observed ones.
Yeah.
So what is the point of all this?
Well, I mean, people, to be fair, people have done things that are a little bit more complicated than just looking, let's say, at one variable. For example, people have looked at lambda, the cosmological constant, and the initial value of the perturbations. So you can look in this two-dimensional thing. And because, for example, you can have a larger lambda if you have a larger amplitude of perturbations initially, and so on. So they have mapped regions in these subparameter spaces. There are some things which we think are really constants of nature because we can observe them to any distance and measure them, and so on, to very high precision, or they come out directly out of some theories and so on. So you can map out some regions of parameter spaces and say, okay, you have to be in this region. And yes, each one of them can vary somewhat in that region, but they're still limited in some, into some more multidimensional, 3, 2, 5, however many dimensions where you can do that. Now, that still doesn't explain anything because, as you point out, there are still all these other universes which we know nothing about. So I think that we should, the reason I'm willing to entertain an open mind to this possibility, but I think that until we will actually be able to make some predictions, or, if we're really lucky, we will actually show that we can actually from first principles find out the values of some of these things, then we will really know better. I think that most people, by the way, most physicists, even probably the strongest supporters of the multiverse idea, I still think that they would rather find some first principle explanation to all these things instead of the multiverse. It's just because that they think that they cannot, that they say, okay, I'm going to entertain the possibility of a multiverse.
Yeah, the reason, to take your example of the fact that the dark energy, the lambda parameter, cannot be too large, that's fine. If you can counterbalance that by having larger initial fluctuations, but at some point you produce too many black holes or whatever.
That's right.
So that's your limit. On the other hand,
so it limits
but only it limits it from above. There's no guarantee there has to be a dark energy from that, because once you allow the dark energy parameter to be smaller, it can be very small, it could be 0, and it could even be negative. In fact, if it's negative, that actually helps structure form. So you have a huge parameter space to fill up there. What have you really gained? It's just one more observational selection effect, basically, that rules out.
Well, I don't know what you have gained. I think the main question still remains, is there some way for me, like people have tried naively to do, to say, where lambda, that's the energy of the physical vacuum. So let's calculate that. Well, it turns out we cannot calculate that, because when you try to calculate that, however you know to calculate, by summing up many, many modes, you get ridiculous values, which just are completely wrong. So that tells you that that's not the right way of calculating it. Now, you may say, well, I have still not found out the way to calculate that. Or what they would say, no, there is no way to calculate that from first principle. It's just a random variable.
Well, look, maybe we just know too much. Was it in 1916? Einstein got it right? He had lambda in his initial 17, thank you, in his initial field equations. And he didn't quite have the right model of the universe. He put it in for some other purpose, but he did show generically that there it was, a totally natural thing to put into the equations.
And it would have been great if actually, that we can put in Einstein's field equations, we can put lambda on the left-hand side or on the right-hand side. You put it on the left-hand side, it's part of the geometry. If you put it on the right-hand side, it's part of the momentum energy tensor. Right? It's part of the energy density of the universe, right? Right now, we think of it more in terms of part of an energy density, right? It would have been great if somebody could show that somehow the geometry, has to have this thing in it. But nobody has. So, so we're treating it as this energy. And since we know that there is an energy to the vacuum, because that we have measured by the Casimir effect, by lamp shift, energy shifting of energy levels in the hydrogen atom, there has to be an energy of the vacuum there. And lambda is that. The only question is, why does it have the peculiar value that it has?
Yes, so Einstein famously said this was one of the greatest blunders of his life. Do you think he was overreacting somehow?
I think his blunder was to take it out,
yes,
and not to put it in.
Yes. Mm-hmm.